And so that's that's our sigma y, sorry. Our sigma y is 3.825. And then our new sigma x, I've rotated 15 degrees. That'll come out to be 11.165. And our new shear stress is equal to 2.933. So yeah, let's just throw these on here real quick. This will be 3.835, 11.165, and 2.933. And so those are pretty cool equations. We actually find that as we do that, we originally thought 10 psi was our maximum, right? Because that was the most that we saw when we found our stresses on that element. But when we just rotated a little bit, we found that this component actually goes up. This stress is now 11.165 along a different axis. So that's pretty cool. But now we still don't even know that that's our maximum, because these equations don't necessarily find the maximum. So let's do that now. Now that we've done that, look at these, we're going to move on. And I'm going to erase this, and we're going to talk about the maximums now. And yeah. So now with that same stress element, let's talk about how we find the principal stresses, the maximum normal stresses in our stress element. And so how we do that is we have another equation where the principal stresses, I'm going to call it, let's just write it, the principal stresses, and those are your maximum and minimum normal stresses that you have. Or, well, I guess not necessarily minimum, but it'll show you your maximum and then the other one that's being applied there. And so that equation will come out to be sigma x plus sigma y over 2 plus or minus, and that plus or minus will give you your y and your x component. Okay, so that plus or minus sigma x, sigma x minus sigma y over 2, the square root of that plus, or squared, plus the shear of xy squared. So take a look at that. It's sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus the shear squared. And so if you plug in the same stuff, you will find that your maximum or your principal stresses are equal to or is it? Yes, your principal stresses are equal to 3.595 and 11.4051, and that's in psi. And so we find that our maximum is quite a bit more than 10 psi, like we saw up in this other one. It's actually more. It's 11.4, which is even more than the other element that we're looking at when we rotate it just a little bit. And so the cool thing about principal stresses is principal stresses occur at the point where there is no shear stresses. So this stress element, if we were to draw it, would just have these elements, but the shear element would go to 0. But we want to find out as well how much we have to rotate it, where that's oriented. And so if we wanted to do that, we can do that by using the equation, the tangent of 2 theta, now theta is the angle that we're looking for, is equal to the shear over sigma x minus sigma y over 2. So your shear over that thing is equal to 2 theta, or the tangent of 2 theta. So you take the arctangent of all that divided by 2, and we find that these principal stresses are oriented along the angle, what was it? 25.1 it looks like. Yeah. Degrees. So we got to rotate this this element 25.1. And so it would look like this. And we'd have the principal stresses and no shear stress, because at the maximum, at the principal stress of the maximum normal stresses, there is no shear stress. We get 11.4 and 3.6 psi. So those are our principal stresses. That's how we find the maximum normal stress on the element, by rotating it that much. Now when we want to find the maximum shear, it's the same type of thing. You have another equation where the shear is equal to the square root of sigma x minus sigma y over 2 squared plus the shear squared. Yeah, and so we plug in those equations, we find that the maximum shear stress in our element has got to be equal to about, what was it? Maximum shear is equal to 3.9, I think it was, yeah. Is 3.905 psi. And along that same, the normal stresses don't disappear like they do with the principal stresses, but where the shear stress is maximum, your normal stresses are going to be equal. It's actually going to be the average of the stresses. So if you were to take these two stresses and you were to average them, which would actually come out to 7.5, because 10 plus 5 divided by 2, that's 7.5. So thereby we know that the x and y, the normal stresses, are both 7.5 psi. We want to find out how much we have to rotate it, and to do that we do a similar equation as to the last one, where tangent of 2 theta is equal to sigma x minus sigma y over 2 divided by the shear. And so that's a lot like the last equation we looked at for the normal stresses. It's just flipped upside down. And so we find that the angle theta, we have to rotate that to find that, has got to be equal to, let's erase this 15, has got to be equal to negative 19.9 degrees. So we got to rotate the other direction 19, or about 20 degrees, and that would find us our where the in-plane maximum shear stress is located, which would look something like this. That's a terrible drawing of a square, but you have all your normal stresses are 7.5, and then you have a shear stress of, what is it, 3.905. And yeah, so that's pretty simple. The equations actually come from something called Moore's circle, which we'll talk about a little bit later, but if we use those equations, we should be able to find out what our maximum things are. So that way we can better anticipate how our piece, or how, if we were to actually make something, we could anticipate how much stress it could actually hold, because we need to know what the maximums are to do that. And so that's a basic overview of what your principal stresses are and your in-plane maximum shear stress, how to find those, and how to use those. And so yeah, there you go.